and I come here from University of New Haven, Connecticut. So my talk will be about the earliest times of the universe, Big Bang, and inflation. So general relativity describes gravity as a curvature of space-time. However, it has several problems. Well, the biggest problem is the problem of singularities, where the matter has infinite density. Also, we know that general relativity is incompatible with quantum mechanics, and possibly quantum gravity could resolve the singularity problem. However, field equations in general relativity they have a symmetric energy momentum tensor, which means they predict the conservation of orbital angular momentum for a free particle. However, we know that Dirac equation, which is relativistic quantum mechanics, predicts the conservation of total angular momentum of elementary particles, orbital plus spin. And so separately orbital and spin don't have to be conserved, and this cannot be done within general relativity, which means general relativity has to be extended, and the simplest extension is called Einstein-Cartan theory of gravity, which was actually started in 1921, 1922. So it's older than Schrödinger's equation. And actually, I have to mention the first director of Center for Astrophysics, Professor George Field. He wrote, like a long time ago, a paper on Einstein-Cartan gravity, and also another professor, Rosanne Di Stefano, also was involved in torsion. So, yeah, it is a nice subject, although it's little underexplored, I would say. So I find it fascinating that we can still do something about this. The problems of Big Bang cosmology and inflation. So, of course, Big Bang singularity. What caused the Big Bang and what existed before? Well, this could be a philosophical question also. Now, about inflation. So inflation is a very successful scenario which explains horizon and flatness problems, and also the observed patterns in CMB. But what caused inflation? Well, most used assumption is scalar fields, although there are some problems with like single scalar fields. So there's like a lot of models of inflation, and they used like several free parameters. Now, also there's a problem how inflation ended. Yeah, because like chaotic inflation would cause eternal inflation, so the universe would be inflating forever, and we know it did not. So I want to show you that Einstein-Cartan theory does several things. It can remove the singularity at the Big Bang and replace Big Bang with Big Bounce, before which the universe was contracting from something. And also the dynamics immediately after the bounce can solve horizon and flatness problems. This is the generic feature of bouncing cosmologies, but also we can generate inflation from torsion. So here's Einstein-Cartan, actually Einstein-Cartan-Sciama-Kibble theory. In the 60s, Sciama and Kibble actually used Einstein-Cartan to Dirac fields. So basically, here's a fine connection, which is the quantity in general relativity used to do calculus on curved space. And Einstein assumed it is symmetric, which means he imposed some constraint. And Cartan said, why to impose constraint? Just let it be whatever it wants to be, from the principle of least action. So adding torsion to gravity is not putting extra thing into theory. It is actually removing one constraint. So it is more natural. So here's a torsion tensor, antisymmetric part of the affine connection. So by varying the Lagrangian, which is the simplest possible Lagrangian, it is proportional to Ricci's scalar. But now we have torsion. We get Cartan equations, and torsion is proportional to the spin density of fermions. And actually, so it is nice because in vacuum, if there is no fermions, then there is no torsion. So Einstein-Cartan reduces to general relativity, and basically Einstein-Cartan passes all the tests which are in observation, and torsion becomes significant only at very high densities, much higher than neutron star densities. So basically, torsion is only relevant when we have to fix general relativity to remove the singularity problem. So here are Cartan equations. Here are Einstein equations. So Einstein tensor. There are some corrections to energy momentum tensor. well, those corrections initially were on the left-hand side of equations. There were corrections to curvature tensor, but using Cartan equations, we can put them on the right-hand side. So basically, we have spin corrections to energy momentum tensor, effectively. And now, macroscopically, Dirac fields can be averaged as spin fluid. So here are the properties of spin fluid. And when you substitute this spin tensor approximated as a spin fluid to Einstein-Cartan equations and write them for homogeneous and isotropic universe, we get Friedmann equations. But you see that in Friedmann equations, there are some corrections to energy and pressure coming from averaged value of the square spin, so it's not zero. Even for random orientations of spin, it's not zero. And this is negative correction to energy density, which means, and it is also quadratic. It is quadratic in number density of fermions, which means when universe is very, very dense, this term, the negative term, grows more. Can be dominant and can cancel the energy density term. So basically, we could have here zero, and basically this negative term manifests itself as gravitational repulsion. And basically, with this equation, the scale factor cannot reach zero. So the Big Bang singularity is avoided, which was found in 1970s by Trautmann, Kopczynski, Hell, and others. So it was like a odd result. So basically, when we combine those two Einstein-Cartan equations with particle production, we get this equation, and this is basically here from the first Friedmann equation. We can find out what is the maximum value of the growth of A dot, of the growth of the scale factor. So we can plug in it here. And now, to avoid eternal inflation, this term cannot be negative, because if it is, then we would get the growth of temperature of the universe with the growth of the universe. So that's not logical. Temperature goes down when scale factor goes up. So basically, this condition that this term has to be bigger than zero basically gives us the maximum value of the particle rate production coefficient. And basically, when this particle rate production coefficient is very close to this value, which is, actually, when it's a numerical value, it depends on the thermal degrees of freedom of all the particles. So we have to know how many particles we know, and in the early universe, we may have more particles. So assuming standard model particles exist only, we have this number. So basically, for the particle production just below this critical value, we discover that temperature is approximately constant, and the expansion is here. This is constant value, so this is constant Hubble parameter. So we have exponential growth, we have inflation. However, it does not last forever, because at some point, when the universe becomes bigger and bigger, then number of fermion density will go down. So effects of the spin will decrease, and basically eventually torsion will be weak, and the Einstein-Cartan will basically reduce to general relativity. So inflation does not last forever. So basically, we don't have eternal inflation. And inflation basically ends. Now here, so basically, now what happens? If you have closed universe, let's assume universe is closed. Universe which is closed would like to, without dark energy, would like to reach the maximum size and go to the small scale factor. Now we have the bounce. Torsion will avoid zero. So we would have, without particle production, we would have universe which is cyclic, but without singularity. But now, with the particle production, the universe basically at each bounce there is more matter, so each cycle is larger and larger, and at some point, universe can reach the size where dark energy can dominate, and basically, after several bounces and cycles, universe will escape the cycles and will expand to infinity. So this was done by Bondi, actually, in the 60s, this analysis. So basically now, just to finalize, with my colleague, Dr. Chantal Desai, we integrated those two equations. We found that number of bounces depend on this particle production rate. So near the critical value, we have on one bounce, but if the particle production rate is a little smaller, well, we get more bounces because we get more bounces, and here's a nice diagram showing that basically initial value of the scale factor is not too much important for the analysis. It is the particle production rate, which tells us, for example, how many e-folds of inflation we have. And actually, here's like a little footnote that, well, if the initial size of the universe is not important, well, it could have originated inside a black hole, which is like the idea which was done in 1970s by Patria Smolin. I was playing with this like 5 years ago, and so who knows, maybe universe originated in the interior of a black hole. The initial size of the universe is not important, well, it could have originated inside a black hole. So who knows, maybe the universe originated in the interior of a black hole.